So now we will look at how to find eigenvectors. Okay, so here I'm going to dive right into an example. This is typically how you'd see a problem phrased. Find all the eigenvalues and eigenvectors of a given matrix. For this example, though, it's going to be a matrix we've already done some work on. So the matrix is this. We're going to start with this 2 by 2 matrix, 3, 0, 8, and minus 1. So that's the matrix that's the very first one we looked at for an example. So as a result, we've actually already done some of the work on this problem. So if we were going to start by finding the eigenvectors, or the eigenvalues, the first thing we would compute is lambda I minus a, which we have already computed. So I'm just going to remind you what that was. Scroll back in your notes to the previous page or so earlier in this section, and you'll be reminded that lambda I minus a in this case was given by this matrix here that I'm writing down, this 2 by 2. So that's lambda minus 3, 0, negative 8, lambda plus 1. That's our lambda I minus a. So, and we also had eigenvalues. Lambda equals 3 and lambda equals negative 1 are the eigenvalues of A. So that's basically a summary of the work we've already done. And you might be wondering, well, why did I bother reminding you of this? We already have the eigenvalues. Well, you're actually going to use this expression now to find the eigenvectors. So that's the reason for bringing this up again. So to find the eigenvectors, you're going to do it for one eigenvalue at a time. So I'm going to I like to put in brackets which eigenvalue I'm working on at each time. So then the rest of the work, you can be reminded that you're working with the eigenvalue lambda equals 3. So what you're going to do is you're going to solve the associated homogeneous system. So what you want to do is solve this system. You want to solve lambda I minus a x equals 0. You're solving the associated homogeneous system to this matrix, but where lambda is equal to 3. And this I'm actually not going to write down over and over again in the future. This is just an extra comment for this particular time. So what you're going to do is you're going to write down lambda I minus a, but when lambda is equal to 3. So, and I'm going to actually write one more comment down here, just a little note so you can see where this is coming from. This is the augmented matrix of this matrix equation. So this is what we're actually going to be wanting to consider. But here, what I'm going to do is I'm actually going to plug in lambda to this expression, and then we're going to write the result down here. So if I plug in 3 to this matrix, I'm going to get 0, 0, negative 8, and 4. And then my constant column, it consists of zeros because I have, I could write a 0 vector there just to be clear. But that's what you're going to get. So because we got zeros on the right-hand side, that's why you have zeros here. Okay, so now the question is, what's the general solution to this system of equations? Because that's really what this can be thought of, right? It's an augmented matrix. You can interpret it as a system of equations that you need to solve. So your first step will be to row reduce it. And I'm not going to show you every detail, but roughly speaking, what you would do is you would first interchange rows 1 and row 2 to get the zeros on the bottom. And then you would multiply the new row 1, which is currently your row 2, by negative 1 over 8. And that would turn this into a matrix that's in reduced row echelon form, and you'd end up getting this matrix. 1, 1/2, 0, 0, 0, 0. Pardon me, 1, 1/2, 0, and 0, 0, 0. So that's what you'd end up getting. And then now you can write down the general solution. Just make up variable names here for each column. I'm just out of habit, I like to call them x1 and x2, and just solve this like you normally would. You've got a leading 1 in the upper left entry, so that means x2 corresponds to a column that doesn't contain a leading 1. So you're just going to give it a parameter. So you let x2 be equal to s, and then you'll write out the equation for x1, which gives you x1 minus 1/2 x2 is equal to 0, or in other words, you get x1 is equal to 1/2 x2, which is equal to 1/2 s. So that gives you the solution for x1. And now what we're going to do is we're going to summarize your solution to this system in column form. So the general solution is given by x, the vector now. I'm going to write x1 was 1/2 s, and x2 was s. So if I pull out an s, which you often will do, I'll get s times 1/2 times 1. And really what you've got here is the general solution now to the associated homogeneous system with lambda I minus a for the particular value of lambda given by lambda equals 3. This is your general solution. And to be very clear, I should say where s is an arbitrary real number, because it's a parameter. It could be absolutely anything, and you'd still get a solution to this system. So let's remind the reader of this down here, where s in the reals is arbitrary. So this is the general solution, but typically what you want to do is you're just interested in one solution. One solution is often good enough if you just want to get an eigenvector corresponding to the eigenvalue lambda equals 3. So what sometimes you might do is you might just say, well, just take s equal to 1, which is equivalent to just ignoring it, because if I multiply a vector by 1, I don't change it. So if you took s equal to 1, you would just get this for your eigenvector. And that's certainly an option. You could do that. Another option, though, which is what is more typically done, is you'll just choose a convenient value of your parameter that would clear the fractions. Like, for example, you might not want to work with that 1/2 if you can avoid it. So what I'll do here is I'll say I'm taking s equal to 2, but you're more than welcome to just take s equal to 1 or -4 or the square root of 2 or any number you want absolutely at all, and you would still get an eigenvector. But I'm going to choose a value that just makes this work out as convenient as possible. So I'm going to take s equal to 2, and then we're going to get x equal to 1, 2, because that's what this evaluates to. If I plug in s equals 2, 2 times 1/2 is 1, and 2 times 1 is 2. So that's the eigenvector I would get. So that's my eigenvector that corresponds to lambda equals 3. And hey, you might have noticed that that's exactly what we got in the first example. Where is the other page? Now I don't know what I did with it. I'll find it in the next clip.